There is a distance so vast, so strange, that even the speed of light seems to crawl when measured against it. We call it a parsec. And if you have ever wondered how astronomers truly map the heavens, this is the unit that makes it possible. But here is the thing. The parsec was not invented to make things easier. It was invented because nothing else worked. Not miles, not kilometers. Not even the famous light year could do the job when scientists needed real precision. The parsec is the ruler of the cosmos. And tonight, we are going to understand exactly what it means, why it exists, and how it reveals distances that no human mind was ever built to imagine. If you find yourself curious about the deepest mysteries of space, take a moment now to like this video and subscribe to the channel. Your support helps us continue exploring the universe together, one wonder at a time. Let us begin with a simple question. How do you measure the distance to something you cannot touch? On Earth, this is easy. You grab a tape measure, you walk the length, you count your steps. But what happens when the thing you want to measure is so far away that walking would take longer than the entire history of human civilization? What happens when even light itself needs years to make the journey? This is the problem astronomers faced when they first turned their telescopes toward the stars. They could see these tiny points of light scattered across the night sky. They could map their positions. They could even measure how bright they appeared. But they could not tell how far away they were. And without knowing the distance, everything else became guesswork. Think about it this way. Imagine you are standing in a dark field at night. You see two lights in the distance. One appears bright, one appears dim. Which one is closer? The obvious answer seems to be the bright one. But that is not necessarily true. The bright light might be a powerful searchlight miles away. The dim light might be a candle just a few hundred feet from where you stand. Without knowing the actual strength of each light source, you cannot determine distance from brightness alone. This was the exact problem astronomers faced with stars. Some stars that appeared dim were actually massive giants, located at enormous distances. Some stars that appeared bright were actually small, faint suns that happened to be relatively close. The sky was a puzzle with no scale, a map with no distances marked. The first attempts to solve this problem used familiar units. Miles seemed like a reasonable choice. After all, we measure everything else in miles. Roads stretch for miles. Countries span thousands of miles. Even the circumference of our own planet can be expressed as roughly 25,000 miles. Surely, miles could handle the distance to the stars. But the numbers quickly became absurd. The nearest star beyond our Sun sits at a distance of approximately 25 trillion miles. Write that number out, and you get a string of digits so long that it loses all meaning. 25 trillion. That is a 25 followed by 12 zeros. Try to imagine that distance. Your brain simply cannot do it. The number is too large to hold any real meaning. Kilometers offered no improvement. In fact, they made things worse. Since a kilometer is shorter than a mile, you needed even more of them to express the same distance. The nearest star became roughly 40 trillion kilometers away. The numbers just kept getting bigger and more meaningless. Clearly, using Earth-based units to measure cosmic distances was like using inches to measure the distance between cities. Technically possible, practically useless. Astronomers needed a new unit, something larger, something that could compress these enormous numbers into figures that a human mind could actually work with. The first solution was the astronomical unit, often written as AU. This unit was based on something very familiar, the distance from Earth to the Sun. 1 astronomical unit equals the average distance between our planet and its star, roughly 93 million miles or 150 million kilometers. This was a good start. Instead of saying Mars is 142 million miles from the Sun, you could simply say Mars orbits at about 1.5 AU. Instead of memorizing strings of zeros, you could work with small, manageable numbers. The astronomical unit worked beautifully within our solar system. Mercury sits at about 0.4 AU from the Sun. Venus orbits at 0.7 AU. Earth, by definition, sits at 1 AU. Mars circles at 1.5 AU. Jupiter swings far out at 5.2 AU. Saturn floats at nearly 10 AU. Uranus and Neptune push even further, at about 19 and 30 AU respectively. Even Pluto, that distant dwarf planet at the edge of our solar neighborhood, sits at an average of roughly 40 AU from the Sun. These are numbers you can actually picture. You can imagine something being 5 times further from the Sun than Earth. You can conceive of something being 30 times further. The AU made the solar system feel comprehensible. But here is where the problem arose. The astronomical unit completely falls apart once you leave the solar system. Remember that nearest star I mentioned, the one sitting 25 trillion miles away. Expressed in astronomical units, that star is approximately 270,000 AU from Earth. We are right back to enormous, meaningless numbers. The AU had taken us from trillions to hundreds of thousands, which is an improvement, but not nearly enough. We needed something even bigger. Enter the light year. This is probably the unit you have heard most often when people talk about cosmic distances. A light year is defined as the distance that light travels in 1 year. Since light moves at roughly 186,000 miles per second, and since a year contains about 31.5 million seconds, you can calculate that light covers approximately 6 trillion miles in a year. 6 trillion. That is the length of one single light year. Now suddenly, that nearest star can be described in a much simpler way. It sits about 4.24 light years from Earth. 4.24. That is a number you can actually say. That is a number you can write without running out of space on the page. The light year became popular because it carries a built-in sense of time. When you hear that a star is 4 light years away, you immediately understand that the light you see tonight actually left that star 4 years ago. When you look at a galaxy 50 million light years distant, you are seeing that galaxy as it existed 50 million years in the past. The light year connects distance and time in a way that feels intuitive. It tells a story. It reminds us that looking out into space is the same as looking back in time. So why did astronomers need anything else? If the light year works so well for public communication, why invent another unit? The answer lies in how astronomers actually measure distances in the first place. The light year is a derived unit. It depends on knowing how fast light travels and how long a year lasts. But when you are trying to determine the distance to a star for the very first time, you do not use the speed of light. You use something far more ancient. You use geometry. Specifically, you use a technique called parallax. And parallax does not give you an answer in light years. It gives you an answer in a completely different unit. A unit that emerges naturally from the measurement process itself. That unit is the parsec. The word parsec is not some arbitrary name pulled from science fiction. It is actually a combination of 2 other words, parallax and arcsecond. To understand what a parsec really means, we need to understand both of these terms. Let us start with parallax. Hold your thumb out in front of your face at arm's length. Now close your left eye and look at your thumb with only your right eye. Notice where your thumb appears to be relative to the background. Now switch. Close your right eye and look with only your left eye. Your thumb appears to have jumped. It seems to have moved against the background, even though you held it perfectly still. This apparent shift is parallax. It happens because your two eyes are located in slightly different positions. Each eye sees your thumb from a slightly different angle. Your brain usually combines these two views to create depth perception. But when you alternate between eyes, you can observe the shift directly. Now, here is the key insight. The amount your thumb appears to shift depends on how far away it is. Try the same experiment with your thumb held very close to your face. The shift is dramatic. Now extend your arm as far as it will go and try again. The shift is smaller. Move your thumb even further away, say by asking a friend to hold something across the room, and the shift becomes tiny. The further away an object is, the less it appears to shift when you change your viewing angle. This relationship between apparent shift and actual distance is the foundation of parallax measurement. Astronomers realized they could use this same principle to measure the distances to stars. But there was a problem. The stars are so incredibly far away that the tiny distance between human eyes produces no measurable shift at all. Even if you could spread your eyes to opposite ends of a football field, the parallax shift of even the nearest star would be too small to detect. Astronomers needed a much bigger baseline. They needed to observe from two positions that were very far apart. And fortunately, Earth itself provided the solution. Every year, Earth completes one full orbit around the Sun. In January, our planet sits on one side of its orbital path. 6 months later, in July, Earth has traveled to the opposite side. The distance between these two positions is approximately 2 astronomical units, or about 186 million miles. This is the largest baseline available to astronomers without leaving our planet. By observing a star in January and then observing the same star again in July, astronomers can look from two positions separated by the full width of Earth's orbit. If the star shows any apparent shift against the background of more distant stars, that shift can be measured and used to calculate distance. The geometry is elegant. Imagine a very long, very thin triangle. At one corner, place the star you want to measure. At the other two corners, place Earth's position in January and Earth's position in July. The baseline of this triangle, the side connecting the two Earth positions, is about 2 AU long. The angle at the star's corner is the parallax angle. It represents how much the star appears to shift when viewed from opposite sides of Earth's orbit. If you know the baseline and you can measure the angle, basic geometry allows you to calculate the length of the other sides of the triangle. Those sides represent the distance from Earth to the star. This brings us to the second word hidden inside Parsec, arcsecond. An arcsecond is a unit of angular measurement. To understand it, we need to start with something more familiar. A full circle contains 360 degrees. You probably learned this in school. If you spin around completely, you have rotated through 360 degrees. Now, each degree can be divided into 60 smaller parts, called arcminutes. And each arcminute can be divided into 60 even smaller parts called arcseconds. So 1 degree contains 60 arcminutes, and 1 arcminute contains 60 arcseconds. This means 1 degree contains 3,600 arcseconds. An arcsecond is tiny, incredibly tiny. If you held up a coin at a distance of about 2.5 miles, the width of that coin would span roughly 1 arcsecond of arc across your field of view. To spot something that small, you would need a telescope. The human eye cannot resolve details at the arcsecond level. This gives you some sense of how precise astronomical measurements need to be. The parallax angles astronomers are trying to detect are measured in fractions of arcseconds. These are shifts so small that they required centuries of technological development before anyone could measure them reliably. Now we can finally define the parsec. A parsec is the distance at which a star would show a parallax angle of exactly 1 arcsecond when observed from opposite sides of Earth's orbit. Let that sink in for a moment. We are defining a distance based on an angle. Specifically, we are defining it as the distance at which a baseline of 1 AU would subtend an angle of 1 arcsecond. The math works out so that 1 parsec equals approximately 3.26 light years. That is about 19 trillion miles or 31 trillion kilometers. The parsec is enormous. It dwarfs any distance we encounter in daily life. But here is why the parsec is so useful. When astronomers actually go out and measure the parallax of a star, the calculation to get distance becomes trivially simple. If a star shows a parallax of 1 arcsecond, it is 1 parsec away. If a star shows a parallax of half an arcsecond, it is 2 parsecs away. If a star shows a parallax of 1/10 of an arcsecond, it is 10 parsecs away. The relationship is beautifully direct. Distance in parsecs equals 1 divided by parallax in arcseconds. No conversion factors needed, no complicated formulas. The parsec was designed to make the math easy. This is why professional astronomers prefer parsecs over light years. The light year might be more intuitive for the general public, but the parsec connects directly to how distances are actually measured. When you see a distance given in parsecs in a scientific paper, you know that distance came from an observation. You know someone pointed a telescope at the sky and measured an angle. The parsec carries the fingerprint of its own measurement method. It is not just a convenient number. It is a record of how we learned what we know. The history of parallax measurement stretches back centuries, filled with failed attempts and frustrating near misses. Astronomers knew the technique should work in principle. They understood the geometry. But for the longest time, no one could actually detect the parallax shift of any star. The angles were simply too small. The instruments were not precise enough. Star after star was observed, and star after star showed no measurable parallax at all. Some people used this failure to argue that the Earth must be stationary. If Earth really orbited the Sun, they said, we should see the star shift as our viewing angle changes. The fact that no shift was detected seemed to prove that Earth stood still, at the center of the universe. But others realized there was another explanation. What if the stars were simply so far away that their parallax angles were smaller than anyone had imagined? What if the universe was vastly larger than the human mind wanted to accept? The breakthrough finally came in the 1830s. A German astronomer named Friedrich Bessel succeeded in measuring the parallax of a star called 61 Cygni. This star had been identified as a good candidate because it showed unusually high proper motion, meaning it moved noticeably against the background stars over time. Such motion suggested the star might be relatively close, and closer stars should show larger parallax angles. Bessel's measurements revealed a parallax of about 0.31 arcseconds. Using this value, he calculated that 61 Cygni sits roughly 10.5 light years from Earth. For the first time in history, humanity knew the actual distance to a star other than the Sun. Almost simultaneously, 2 other astronomers achieved similar results for different stars. Thomas Henderson measured the parallax of Alpha Centauri, and Friedrich Georg Wilhelm Struve measured the parallax of Vega. the race to measure stellar distances was on, and parallax was the winning method. Over the following decades, astronomers refined their techniques and measured the parallax of more and more stars. Each new measurement added another pin to the map of the cosmos. Each new distance revealed just how vast the universe truly was. The nearest star system to our Sun is Alpha Centauri. This is actually a triple star system, containing two Sun-like stars locked in orbit around each other, plus a smaller red dwarf called Proxima Centauri that orbits the pair at a great distance. Proxima Centauri is currently the closest star to Earth, sitting at about 1.3 parsecs away. That translates to roughly 4.24 light-years, or about 25 trillion miles. When you think about that distance, remember that this is the nearest star. Everything else is even further. Most stars visible to the naked eye sit tens, hundreds, or even thousands of parsecs from Earth. The galaxy stretches across roughly 30,000 parsecs from edge to edge. The parsec also comes with convenient larger units for measuring truly cosmic distances. A kiloparsec equals 1,000 parsecs. This unit is useful for describing distances within our own galaxy. The center of the Milky Way, for example, sits about 8 kiloparsecs from Earth. That is roughly 26,000 light-years. When astronomers talk about the structure of our galaxy, they often use kiloparsecs because the numbers stay manageable. The spiral arms of the Milky Way span several kiloparsecs across. The halo of old stars surrounding the galactic disk extends tens of kiloparsecs in every direction. Beyond our galaxy, distances grow even more extreme. This is where the megaparsec becomes useful. A megaparsec equals 1 million parsecs. The Andromeda Galaxy, our nearest large galactic neighbor, sits about 0.78 megaparsecs away. That is roughly 2.5 million light-years. The Virgo cluster, a Dartic great collection of thousands of galaxies, lies about 16.5 megaparsecs from the Milky Way. The Coma cluster, another massive galaxy gathering, sits at roughly 100 megaparsecs. When astronomers map the large-scale structure of the universe, measuring the distances between galaxy clusters and the great walls and voids of the cosmic web, they think in megaparsecs. For the very largest scales, we need the gigaparsec. A gigaparsec equals 1 billion parsecs. The observable universe stretches roughly 14 gigaparsecs in radius. That means the most distant light we can see originated about 14 billion parsecs away. Beyond that horizon lies more universe that we simply cannot observe because light from those regions has not had time to reach us since the beginning of time. The gigaparsec is a unit so large that it encompasses not just our galaxy or our local cluster, but significant fractions of everything that exists. Let us pause here and truly grapple with what these numbers mean. When I say that Proxima Centauri is 1.3 parsecs away, that might sound like a small number. 1.3, barely more than 1. But remember what a parsec actually represents. 1 parsec is about 19 trillion miles, so 1.3 parsecs is roughly 25 trillion miles. To walk that distance at a normal walking pace would take about 500 million years. To drive it in a car moving at highway speeds would take about 30 million years. Even traveling at the speed of a jet airplane, the trip would take over 3 million years. And this is the nearest star, the nearest one. The Andromeda Galaxy sits 0.78 megaparsecs away. That sounds even more modest, less than 1. But a megaparsec contains 1 million parsecs. So 0.78 megaparsecs is 780,000 parsecs. Multiply that by 19 trillion miles per parsec, and you get a number so large that writing it out would fill multiple lines. This is a distance that light itself takes 2.5 million years to cross. The light reaching your eyes from Andromeda tonight left that galaxy before modern humans existed. It was traveling through the void while our ancestors were still learning to walk upright on the plains of Africa. And the observable universe stretches 14 gigaparsecs, 14 billion parsecs. The number becomes so large that it stops being a number and starts being a kind of philosophical statement. It says that the universe is bigger than any concept the human brain evolved to handle. We did not develop the neural circuitry to imagine such distances. Our minds were shaped by savannas and forests, by distances measured in days of walking, by horizons that sat a few miles away. The parsec reveals just how provincial our intuitions really are. This is why I said at the beginning that the parsec is a distance that defies human understanding. It is not that the concept is complicated. The geometry is straightforward. The math is simple. But the actual size of a parsec, let alone a kiloparsec or megaparsec, exceeds the bounds of what our nervous systems can truly process. We can write the numbers. We can perform the calculations. But we cannot genuinely feel the distance. It remains abstract, a symbol on a page rather than an experience in our bones. Yet this is also what makes astronomy so remarkable. Despite our limitations, despite the poverty of our intuitions, humans have managed to map the cosmos. We have measured distances that we cannot imagine. We have charted structures that we cannot picture. We have sent our understanding far beyond the narrow world that evolution prepared us for. The parsec is both a measure of cosmic immensity and a monument to human ingenuity. It reminds us how small we are, but it also reminds us how far our curiosity can carry us. Let us now return to the mechanics of parallax measurement and understand why this technique eventually runs into limits. Remember that the parallax angle gets smaller as distance increases. A star at 1 parsec shows a parallax of 1 arcsecond. A star at 10 parsecs shows a parallax of 0.1 arcseconds. A star at 100 parsecs shows a parallax of 0.01 arcseconds. The pattern continues. The further the star, the tinier the angle. At some point, the angles become so small that no telescope on Earth can measure them accurately. Atmospheric turbulence causes stars to twinkle and blur. This blurring limits how precisely we can determine a star's position. Ground-based telescopes can typically measure parallax angles no smaller than about 0.01 arcseconds, which corresponds to distances of about 100 parsecs. Beyond that range, the angles are simply lost in the noise. Stars further than 100 parsecs cannot have their distances measured directly from Earth's surface using traditional parallax techniques. This limitation plagued astronomers for over a century. The nearby stars could be mapped precisely. We knew the distances to a few thousand stellar neighbors within about 300 light-years, but the vast majority of stars in our galaxy remained out of reach. The Milky Way contains several hundred billion stars, and we could only measure distances to a tiny fraction of them. The cosmic map had a well-measured local neighborhood, surrounded by an enormous blank area labeled essentially unknown. The solution required getting above Earth's atmosphere. In 1989, the European Space Agency launched a satellite called Hipparcos. This spacecraft was specifically designed to measure stellar parallaxes from space, where atmospheric blurring does not exist. Hipparcos measured the positions and parallaxes of over 100,000 stars with unprecedented precision. It could detect angles as small as about 0.001 arcseconds, pushing the range of parallax measurement out to about 1,000 parsecs. Suddenly, astronomers had accurate distances to stars throughout a significant chunk of the Milky Way's disk. But even Hipparcos was just a beginning. In 2013, the European Space Agency launched an even more ambitious mission called Gaia. This spacecraft is currently still operating, mapping the positions, distances, and motions of roughly 2 billion stars in our galaxy. Gaia can measure parallaxes down to about 20 microarcseconds, or 0.00002 arcseconds. This allows distance measurements out to tens of thousands of parsecs, encompassing a large portion of the Milky Way. The Gaia mission has revolutionized our understanding of the galaxy. It has revealed the three-dimensional structure of spiral arms. It has traced the orbits of stars around the galactic center. It has discovered streams of stars left behind by galaxies that the Milky Way absorbed long ago. All of this comes from parallax, from that simple geometric technique of looking at stars from slightly different angles. The humble principle that allows you to judge depth with your two eyes has been scaled up to map an entire galaxy. Yet even Gaia has limits. At some point, even the most precise measurements cannot detect the tiny parallax angles of the most distant stars. The center of our galaxy sits about 8 kiloparsecs away. The far side of the galaxy is even more distant. Many stars in the Milky Way remain beyond the reach of direct parallax measurement. And when we look beyond our galaxy to other galaxies millions of parsecs distant, parallax is completely useless. The angles are so small that they might as well be zero. This is where the parsec transitions from being the endpoint of measurement to being the starting point for something bigger. Astronomers call it the cosmic distance ladder. The idea is simple but powerful. Use one technique to measure nearby distances with high precision. Then use those nearby measurements to calibrate a different technique that works at greater distances. Then use that technique to calibrate yet another method for even greater distances. Each rung of the ladder builds on the ones below it. Each step outward depends on the accuracy of all previous steps. The parsec, measured through parallax, forms the first rung of this ladder. Without accurate parallax distances to nearby stars, nothing else would work. Every other technique for measuring cosmic distances ultimately traces back to parallax. The parsec is the foundation on which our entire map of the universe is built. The second rung of the ladder involves a special type of star called a Cepheid variable. These are stars that pulsate, brightening and dimming in a regular cycle. In 1912, an astronomer named Henrietta Swan Leavitt discovered something remarkable about Cepheid variables in a nearby galaxy called the Small Magellanic Cloud. She found that brighter Cepheids pulsate more slowly than dimmer ones. This relationship between brightness and pulsation period is incredibly consistent. If you measure how long it takes a Cepheid to complete one cycle of brightening and dimming, you can determine how intrinsically bright that star really is. This discovery was revolutionary. Remember the problem of not knowing whether a light is bright and far away or dim and nearby. Cepheids solve this problem. By watching a Cepheid pulsate, you can determine its true brightness. Then you compare that true brightness to how bright it appears in the sky. The difference tells you the distance. A star that is intrinsically bright but appears dim must be far away. A star that is intrinsically dim but appears bright must be relatively close. Cepheids act as cosmic yardsticks, allowing astronomers to measure distances far beyond the reach of parallax. But here is the crucial connection to the parsec. Leavitt discovered the period-luminosity relationship. but she could not determine the actual scale. She knew that slow Cepheids are brighter than fast Cepheids, but how bright exactly? To answer that question, astronomers needed to know the distance to at least one Cepheid variable. And how do you measure the distance to a star? Parallax. Astronomers identified Cepheid variables close enough to Earth that their parallax could be measured directly. Using those parallax distances, they calibrated the period-luminosity relationship. They figured out exactly how bright each type of Cepheid really is. From that point on, any Cepheid anywhere in the universe could be used as a distance indicator, as long as you could measure its pulsation period. Today, Cepheid variables have been observed in galaxies tens of megaparsecs away. BIM. Each measurement relies on the calibration that traces back through parallax to the definition of the parsec. Without that foundation, Cepheid distances would be meaningless. The light from a pulsating star in a distant galaxy travels millions of years to reach our telescopes. We measure its brightness, time its pulses, and calculate a distance. But the entire calculation only works because someone, somewhere, measured a parallax angle to a nearby Cepheid. The parsec reaches across the cosmos through a chain of logic and observation. The third rung of the distance ladder involves an even more powerful tool, type Ia supernovae. These are a particular kind of stellar explosion that occurs when a white dwarf star accumulates too much matter from a companion star. When the white dwarf's mass exceeds a certain threshold, around 1.4 times the mass of our Sun, it can no longer support itself against gravity. The star collapses and detonates in a titanic explosion that can outshine an entire galaxy for a brief period. The remarkable thing about type Ia supernovae is that they all reach roughly the same peak brightness. Because the explosion is triggered at a specific mass threshold, there is a natural uniformity to these events. Every type Ia supernova, anywhere in the universe, produces roughly the same amount of light at maximum. This makes them excellent standard candles. If you see a type Ia supernova in a distant galaxy, you know approximately how bright the explosion truly is. Compare that true brightness to the observed brightness, and you can calculate the distance. Type Ia supernovae are bright enough to be seen across billions of parsecs. They have been used to measure the distances to galaxies near the edge of the observable universe. These measurements contributed to one of the most stunning discoveries in modern cosmology. In the late 1990s, two independent research teams used type EIGA supernovae to study the expansion of the universe. They expected to find that the expansion was slowing down over time, pulled back by the gravitational attraction of all the matter in the cosmos. Instead, they found the opposite. The expansion of the universe is accelerating. Something is pushing the universe apart faster and faster as time goes on. This mysterious push has been named dark energy. No one knows exactly what dark energy is. It might be a property of space itself, a kind of cosmic anti-gravity built into the fabric of the universe. It might be a new type of field pervading all of existence. Whatever it is, dark energy makes up roughly 68% of the total energy content of the universe. And we only discovered it because of distance measurements. We only found dark energy because we could measure how far away certain supernovae were and compare those distances to their redshifts. Trace the logic backward. The supernova distances depend on calibration. That calibration depends on Cepheid variable distances. The Cepheid distances depend on parallax calibration. The parallax calibration defines the parsec. One of the most profound discoveries about the nature of reality, the existence of dark energy, ultimately rests on a geometric technique for measuring angles in the sky. The parsec is not just a unit of distance. It is a link in a chain that connects our backyard to the accelerating expansion of the cosmos. Let us pause and appreciate what we have learned. The parsec began as a solution to a practical problem. Astronomers needed a unit that matched their measurement technique. Parallax naturally gives distances in parsecs, so the parsec became the standard. But this practical origin does not diminish the parsec's importance. Quite the opposite. The parsec is important precisely because it connects to observation. It is rooted in reality. Every distance measured in parsecs carries an implicit reference to the geometry of triangles and the positions of stars. The light year, by contrast, is more abstract. It defines distance in terms of how far light travels in a year. This is intuitive in some ways. It creates a mental link between distance and time. But the light year does not connect to any measurement technique. When astronomers actually determine how far away a star is, they do not time how long light takes to arrive. They measure angles. They calculate trigonometry. The answer comes out in parsecs. Converting to light years is a secondary step, done mainly for public communication. This is not to say the light year is bad or wrong. Both units have their place. The light year is excellent for conveying a sense of cosmic scale to people unfamiliar with astronomical methods. It carries an intuitive meaning that the parsec lacks. But for working astronomers, for people actually doing the measurements and making the discoveries, the parsec is the natural unit. It speaks the language of observation. Consider how this plays out in scientific literature. Open any professional astronomy journal, and you will find distances given in parsecs, kiloparsecs, or megaparsecs. The papers assume their readers understand what these units mean. They do not bother converting to light years because the target audience thinks in parsecs already. The parsec is the insider unit, the language of the field. Light years are for outreach, parsecs are for research. Now let us think about what the parsec reveals about human progress. The first successful parallax measurement happened in 1838. That is less than 200 years ago. Before that date, humanity had no reliable way to determine the distance to any star. We could map the constellations. We could track the planets. We could speculate about cosmic distances, but we did not actually know. The stars could have been relatively close or impossibly far. Without parallax, we were guessing. The 18th century astronomer William Herschel tried to estimate stellar distances using brightness comparisons. He assumed all stars were equally luminous and used apparent brightness to rank distances. This approach was fundamentally flawed because stars vary enormously in intrinsic brightness. Some are thousands of times more luminous than the sun. Others are mere sputtering embers, barely visible even up close. Using brightness alone gives completely wrong answers. Before Herschel, most people assumed the stars were attached to a celestial sphere at some unknown, but probably not enormous distance. The sphere held the stars fixed in their patterns, while rotating once a day around the Earth. This model was elegant and intuitive. It matched what people saw when they looked up at night. But it was completely wrong. The stars are not attached to a sphere. They float in three-dimensional space at wildly varying distances. Some are close enough that their light takes only a few years to reach us. Others are so far away that their light has been traveling since before the Earth existed. Parallax revealed this truth. It showed that the universe is deep. The stars are scattered through an immense volume, not painted on a surface. This was a conceptual revolution as significant as any in the history of science. The universe went from being a room to being an abyss. The sky went from being a ceiling to being a window into infinity. All of this came from measuring tiny angles. All of this came from understanding what the parsec means. The story continues today. Modern parallax measurements from spacecraft like Gaia are revealing details about our galaxy that would have seemed like magic to Bessel and his contemporaries. We can now track how individual stars move through the galaxy. We can identify groups of stars that were born together and have since drifted apart. We can map the gravitational influence of the galaxy's central black hole on the orbits of nearby stars. We can see the remnants of smaller galaxies that the Milky Way has consumed over billions of years. Each of these discoveries builds on the parsec. Each one requires knowing where things are in space, and that knowledge comes from parallax. The more precisely we can measure parallax angles, the more accurately we can determine distances, and the more clearly we can see the structure of our cosmic neighborhood. The parsec is not just a historical artifact. It is a living tool, continuously refined and applied to ever more ambitious goals. Let us now return to the question that opened this exploration. Why does the parsec seem so strange? Why is it described as a distance that defies human understanding? Part of the answer is simply that the parsec is large. Very, very large. But that is true of many units in astronomy. The light year is also enormous. The astronomical unit is also far beyond everyday experience. Size alone does not explain the parsec's peculiarity. The deeper strangeness lies in how the parsec is defined. Most distance units are based on familiar objects or experiences. The meter was originally defined as 1/10,000,000 of the distance from the equator to the North Pole along a line passing through Paris. The foot was based on actual human feet. The inch was originally the width of a thumb. Even the light year, though vastly larger, is based on something we encounter constantly: light. Everyone knows what light is. Everyone has seen light travel across a room or flash across the sky during a storm. The parsec, by contrast, is based on an angle, specifically an angle so tiny that no human can perceive it without instruments. 1 arcsecond is 1/3600th of 1 degree. It is the angle subtended by a human hair seen from about 60 feet away. It is the angle subtended by a quarter seen from over 3 miles away. No one can look at the sky and see an arcsecond. The unit is invisible to human senses. It belongs to the world of telescopes and precision instruments, not the world of naked eye observation. And the parsec is the distance at which this invisible angle corresponds to the width of Earth's orbit. Think about that. You need to imagine a triangle with a base of 186 million miles and an apex angle so small that it takes specialized equipment to measure. The triangle is almost impossibly thin and elongated. Its 2 long sides stretch 19 trillion miles into space, while converging on an angle that occupies less than 1/1,000,000th of the sky. This is the shape that defines a parsec. No wonder it seems strange. The human brain evolved to handle the world at human scales. We are good at estimating distances we can walk in a day. We are good at judging angles that correspond to visible features like the width of the moon, which is about 1/2 a degree, or the angle between 2 mountain peaks on the horizon. We did not evolve any intuition for arcseconds. They are simply too small for our ancestors to have ever needed. When we try to imagine a parsec, we are trying to stretch neural circuitry far beyond its design parameters. Yet we have done it. Somehow, despite the limitations of our biological inheritance, humans have managed to conceptualize, define, measure, and use the parsec. We have taken a unit that makes no intuitive sense and made it the foundation of cosmic cartography. This is the power of mathematics and instrumentation. They extend our reach beyond what our senses can grasp. They let us know things we cannot feel. Consider the earliest astronomers who worked with parallax. They knew the technique should work. The geometry was clear. But when they pointed their telescopes at stars and tried to measure the shift, they found nothing. Star after star showed no detectable parallax. For years, this seemed like failure. The universe was mocking their efforts, refusing to reveal its secrets. But these astronomers did not conclude that parallax was useless. Instead, they concluded that the stars must be incredibly far away. The absence of a measurable shift was not evidence against the technique. It was evidence for the vastness of space. This is a profound intellectual move. They used the failure of observation to constrain reality. If the parallax is too small to measure, then the distance must be too large to produce a measurable parallax. The universe revealed itself through what it refused to show. Eventually, instruments improved. Bessel's heliometer allowed more precise measurements than ever before. He chose a star with high proper motion, reasoning that fast-moving stars might be closer and thus more likely to show measurable parallax. His persistence paid off. 61. Cygni yielded a parallax of about 0.31 arcseconds. The distance could finally be calculated. The universe had given up one of its secrets. The joy of that moment must have been extraordinary. After generations of trying, after centuries of wondering, humanity finally knew how far away a star was. Not an estimate based on assumptions, not a guess guided by intuition. An actual measurement grounded in geometry, expressed in a unit that would come to be known as the parsec. The cosmos was still unimaginably large, but it was no longer completely unmapped. That first measurement was a foothold, a beginning, a crack in the wall of ignorance. Since then, the map has grown continuously. Hundreds of stars became thousands. Thousands became millions. Millions became billions with the Gaia mission. Each new measurement fills in more of the picture. Each parallax angle, however tiny, contributes to our understanding of where things are. The parsec is the unit that holds all of this together, the common currency that lets astronomers combine data from different eras and different instruments into a single coherent map. Let us now think about scale more carefully. I have thrown around large numbers throughout this exploration. Trillions of miles, billions of parsecs. These numbers wash over us without really landing. Let me try a different approach. Let me try to build a sense of scale through comparison. Start with something familiar. The distance from New York to Los Angeles is roughly 2,500 miles. This is a distance that many people have traveled, either by car over several days or by plane in a few hours. It is a substantial journey, spanning a continent, but it is comprehensible. Most adults can imagine driving across the country. They have some sense of what 2,500 miles feels like. Now multiply that distance by 10. 25,000 miles. This is roughly the circumference of the Earth. If you could drive around the entire planet without stopping, this is how far you would go. It would take months of continuous driving. The distance is huge, but still within the realm of human projects. People have sailed around the world. Airplanes circle the globe routinely. 25,000 miles is large, but not unimaginable. Multiply by 10 again. 250,000 miles. This is roughly the distance from the Earth to the Moon. Spacecraft have traveled this distance. Astronauts have made the journey. Light covers it in about 1.3 seconds. We have sent machines and humans to the Moon and brought them back. This distance, while vastly larger than anything encountered in daily life, is still connected to human experience through the achievements of the space program. Multiply by 400, 100 million miles. Now we are approaching the scale of the inner solar system. This is roughly the distance from Earth to the Sun, 1 astronomical unit. No human has traveled this far. No spacecraft has carried people across this gulf. But we have sent robotic probes to every planet in the solar system, machines that have crossed these distances and returned data. The solar system is huge, but it is our home. We have explored it, mapped it, understood it. 100 million miles is the scale of our cosmic backyard. Multiply by 270,000. That gives you the distance to the nearest star. 25 trillion miles. This is where human experience completely runs out. No spacecraft has come close to traveling this distance. The fastest objects ever launched by humanity, the Voyager probes, are creeping toward interstellar space at about 35,000 miles per hour. At that speed, reaching the nearest star would take roughly 70,000 years. This is longer than all of recorded human history. This is longer than the existence of modern humans as a species in some reckonings. And the nearest star is just the beginning. The Milky Way galaxy spans roughly 100,000 light-years, or about 30,000 parsecs. To cross the galaxy at the speed of the Voyager probes would take hundreds of millions of years. The Andromeda galaxy, our nearest large neighbor, sits 2.5 million light-years away. Reaching it at Voyager speeds would take tens of billions of years, longer than the current age of the universe. These numbers are not meant to discourage. They are meant to calibrate. The parsec is a unit designed for these scales. When astronomers say something is 10 parsecs away, they are describing a distance of roughly 32 light-years, or about 190 trillion miles. When they say something is a kiloparsec away, they are describing 3,200 light-years. When they talk about megaparsecs, they are describing millions of light-years. The parsec provides a compact way to express distances that would otherwise require scientific notation and strings of zeros. But the parsec also provides a reality check. It reminds us that the universe operates on scales that dwarf human concerns. Our planet is a speck. Our solar system is a speck. Even our galaxy, with its hundreds of billions of stars, is just one galaxy among hundreds of billions of galaxies in the observable universe. The parsec does not let us forget this. Every time an astronomer uses the unit, they are implicitly acknowledging the vastness of the cosmos. There is a paradox in this acknowledgement. The parsec was created by humans. The measurement technique was invented by humans. The satellites that measure parallax with micro-arcsecond precision were built by humans. We have taken our limited brains and our modest lifespans and somehow assembled a picture of a universe billions of years old and billions of parsecs across. The very unit that emphasizes our smallness is also evidence of our reach. This is what science does. It extends human understanding far beyond human experience. We cannot travel to the stars. We cannot live for billions of years. We cannot directly perceive arcseconds or comprehend trillions of miles. But we can build instruments that measure what we cannot see. We can develop mathematics that describes what we cannot imagine. We can construct theories that explain what we cannot directly experience. The parsec is one tool in this project. It is a way of translating the inhuman scale of the cosmos into something we can at least manipulate, even if we cannot truly feel it. Let me take you through one more layer of the cosmic distance ladder. We discussed parallax, Cepheid variables, and type, EA supernovae. Each technique reaches further into the universe than the last. But there is another method that deserves attention, one that operates at the very edge of the observable universe. It involves the oldest light in existence. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Before that moment, the cosmos was filled with a dense plasma that scattered light in all directions. Photons could not travel far before colliding with particles and bouncing off in random directions. The universe was opaque, like the inside of a fog. But when atoms formed, the fog suddenly cleared. Light could finally travel freely through space. The first, light that could move without immediate scattering, began its journey toward us. That light has been traveling ever since. Over the course of nearly 14 billion years, it has crossed almost the entire observable universe. When it finally reaches our telescopes, it carries information about the conditions of the cosmos when it was first released. This light is called the cosmic microwave background, or CMB. It is the oldest light we can see, and it comes from the furthest distances we can probe. The CMB does not give distances the same way parallax or standard candles do. Instead, it provides a kind of cosmic ruler built into the fabric of space itself. The early universe contained tiny fluctuations in density, small variations in how matter was distributed. These fluctuations left imprints on the CMB, patterns of slightly hotter and slightly cooler regions. The characteristic size of these patterns depends on the geometry of the universe and how it has expanded over time. By measuring the CMB patterns and comparing them to theoretical predictions, astronomers can determine cosmic distances with remarkable precision. They can figure out how far the CMB surface is, and they can use that measurement to calibrate other techniques. The CMB has helped pin down the age of the universe, the rate of cosmic expansion, and the overall geometry of space. All of this feeds back into the distance ladder, cross-checking and refining the measurements made with other methods. The Parsec connects to the CMB through the chain of calibration I described earlier. Parallax calibrates Cephids. Cephids calibrate supernovae. Supernovae and other techniques calibrate models of cosmic expansion. Those models predict what the CMB should look like. When observations match predictions, we gain confidence that our distance measurements are correct. When they disagree, we learn that something in our understanding needs revision. In recent years, there has been exactly this kind of disagreement. Different methods of measuring the expansion rate of the universe give slightly different answers. Measurements based on the CMB suggest one value for the expansion rate. Measurements based on Cephids and supernovae suggest a slightly different value. This discrepancy, called the Hubble tension, is one of the biggest puzzles in modern cosmology. It might indicate that our understanding of the early universe is incomplete. It might point to new physics beyond our current theories. Or it might simply reflect subtle errors in one or more measurement techniques. Resolving the Hubble tension requires better distance measurements, more precise parallaxes, more accurate Cepheid calibrations, more supernovae observed in more distant galaxies. The Parsec sits at the base of all of these efforts. Every improvement in parallax precision ripples up through the cosmic distance ladder, affecting measurements at every scale. The strange unit that defines astronomical distance is also the key to understanding the expansion of the universe itself. Let us bring this exploration toward a close with some reflection. We began with a simple question about how astronomers measure cosmic distances. The answer led us through the history of parallax, the geometry of triangles, the definition of the arcsecond, and the invention of the parsec. We climb the cosmic distance ladder from nearby stars to distant supernovae to the edge of the observable universe. We encountered dark energy, the Hubble tension, and the cosmic microwave background. All of these topics connect through the humble Parsec. The Eden Parsec is not flashy. It does not capture the public imagination the way black holes or dark matter do. When science fiction authors want to convey vast distances, they usually reach for the light year rather than the parsec. But for working astronomers, for the people actually mapping the cosmos, the parsec is indispensable. It is the unit that emerges naturally from observation. It is the foundation on which all other distance measurements rest. There is something deeply satisfying about this. The universe, for all its incomprehensible vastness, yields to human inquiry. We cannot travel to the stars, but we can measure how far away they are. We cannot live long enough to see galaxies drift apart, but we can calculate the rate at which they recede. We cannot directly perceive the structure of the cosmos, but we can build telescopes that see what our eyes cannot, and develop mathematics that describes what our intuitions cannot grasp. The parsec embodies this achievement. It takes the invisible angle of an arcsecond and the invisible baseline of Earth's orbit and combines them into a unit of distance that reaches across the universe. It is abstract, yes. It is hard to visualize, certainly, but it works. It delivers accurate, reliable distances to objects billions of light years away. It lets us map structures that span millions of parsecs. It connects the position of Earth in January to the expansion of the cosmos itself. When you look up at the night sky, you are seeing light that has traveled across parsecs, kiloparsecs, even megaparsecs to reach your eyes. The stars you see are scattered through three-dimensional space at vastly different distances. Some are relatively close, a few parsecs away. Others are thousands of parsecs distant, near the edge of naked eye visibility. The faint smudge of the Andromeda Galaxy, just barely visible on dark nights, sits nearly 800,000 parsecs from where you stand. All of this distance, all of this depth, was once invisible. People looked at the sky and saw a flat canvas of lights. They had no way to know which lights were close and which were far. The parsec changed that. It gave us depth perception for the cosmos. It revealed that the universe is not a painting but a sculpture, not a ceiling but an ocean of space. And yet the parsec also reminds us of our limitations. We can measure these distances, but we cannot cross them. The nearest star at 1.3 parsecs is utterly unreachable with current technology. The far side of the galaxy at 30,000 parsecs might as well be in another universe for all our ability to visit it. The observable universe stretches 14 billion parsecs, an expanse we can map but never explore. The parsec gives us knowledge but not access. It expands our understanding while revealing the boundaries of our experience. Perhaps this is the ultimate lesson of the parsec. Human beings are small. Our lives are short. Our planet is a tiny mote in an incomprehensible vastness. But our minds can reach further than our bodies. We can measure what we cannot touch. We can map what we cannot visit. We can understand what we cannot experience. The parsec is a symbol of this reaching. It is a unit of ambition as much as distance. So the next time you hear a distance given in parsecs, take a moment to appreciate what that number represents. It is not just a measure of how far away something is. It is a record of human effort. It is the culmination of centuries of refinement in instruments and techniques. It is the foundation of our entire map of the universe. And it is a reminder that even the strangest, most incomprehensible distances can be known, measured, and expressed in the language of science. The parsec defies human understanding in the sense that we cannot truly feel it. We cannot imagine 19 trillion miles. We cannot visualize an arcsecond. We cannot grasp what it means for light to travel for years through empty space. But we can understand the parsec in another sense. We can learn how it is defined. We can follow the logic of parallax measurement. We can appreciate the chain of reasoning that connects the parsec to the edge of the observable universe. This intellectual understanding is its own kind of achievement. It may not satisfy our intuitive hunger for direct experience, but it illuminates the cosmos in ways that intuition never could. The universe is vast beyond imagining. The parsec is our ruler for measuring that vastness. It is strange, it is abstract, and it defies easy visualization. But it works. It has carried us from the first uncertain measurements of nearby stars to the discovery of dark energy and the mapping of billions of galaxies. It will continue to serve as astronomers push toward ever more precise observations and ever more distant objects. In the end, the parsec is a gift. It is the gift of distance made measurable, of space made navigable to the mind if not the body. It is the foundation of cosmic cartography, the base unit of the universe's map. And every time we use it, we participate in humanity's greatest intellectual adventure. We join the ranks of those who looked up at the night sky and decided to measure what they saw. We continue the tradition of Bessel and Leavitt and all the astronomers who transform points of light into places in space. The stars are not just lights. They are suns, other worlds, destinations. The parsec tells us how far away they are. That knowledge may seem abstract, but it connects us to the cosmos in a profound way. We are not isolated observers on a lonely planet. We are residents of a universe we can comprehend, members of a species that has learned to see across billions of years and billions of parsecs. The parsec is our proof that understanding is possible. The cosmos is strange, but it is not unknowable. Distances defy our intuitions, but they yield to our measurements. And in that yielding, we find our place among the stars. Thank you for joining us on this journey through the strange distance that is the parsec. If you found this exploration valuable, please consider leaving a like and subscribing to the channel. Your support helps us continue mapping the wonders of the cosmos together. Until next time, keep looking up and remember that every point of light you see has a distance, a story, and a place in the great map of the universe. But before we part ways, let us delve even deeper into some aspects we have only touched upon. The story of the parsec is far from complete. There are nuances and details that deserve attention, corners of this subject that reward careful exploration. Let us continue our journey through the strange geometry of cosmic distance. Consider for a moment the actual mechanics of a parallax observation. I described the basic principle earlier, but the practical reality is far more challenging than the simple description might suggest. Astronomers do not simply point a telescope at a star and read off a parallax angle. The process requires months of careful work, repeated observations, and sophisticated analysis. First, you need reference stars. When you measure the apparent position of your target star, you are not measuring against some absolute grid in the sky. You are measuring relative to the positions of other, more distant stars in the same field of view. These background stars are so far away that their own parallax is essentially zero. They provide a fixed reference frame against which the closer target star appears to shift. This means that every parallax measurement is actually a differential measurement. You are comparing how one star moves against the backdrop of others. If all stars shifted together, you would see nothing. the parallax signal emerges from the difference in motion between nearby and distant objects. The closer star seems to dance back and forth over the course of a year, while the background stars remain still. But getting accurate positions for all these stars is extremely difficult. Telescopes have optical imperfections. The atmosphere bends light in subtle ways. The Earth itself wobbles slightly on its axis, creating small variations in where the telescope points. The mechanical parts of the telescope expand and contract with temperature changes. Each of these factors introduces errors that can swamp the tiny parallax signal you are trying to detect. To overcome these challenges, astronomers developed elaborate procedures. They observed the same field of stars night after night, month after month. They calibrated their instruments obsessively, tracking every possible source of error. They developed mathematical techniques to remove systematic effects from their data. They repeated measurements over multiple years to beat down random noise through averaging. The heliometer that Bessel used was a specialized instrument designed specifically for parallax work. It contained a split objective lens that could be adjusted to bring two different stars into apparent coincidence. By measuring the amount of adjustment needed, Bessel could determine the angular separation between stars with exquisite precision. The technique was tedious and demanding, requiring hours of careful work for each set of measurements, but it delivered results that no other method could match at the time. Even with these elaborate procedures, early parallax measurements were barely at the edge of detectability. Bessel's parallax for 61 Cygni was about 0.31 arcseconds. His measurement uncertainty was probably close to 0.01 arcseconds. This meant the detection was reliable, but not by a huge margin. Stars with smaller parallaxes, further from Earth, would have been lost in the noise. Over the following decades, instruments improved and techniques were refined. Photography replaced visual observation, allowing more precise position measurements and permanent records that could be analyzed later. The photographic plate became the astronomer's primary tool for parallax work, capturing the positions of hundreds of stars in a single exposure. By the middle of the 20th century, photographic parallaxes had been measured for several thousand stars. Most of these were within about 100 parsecs, the practical limit of ground-based observations. Beyond that distance, the parallax angles were simply too small to measure reliably through the shimmering atmosphere. The atmosphere deserves special mention as an obstacle. You may have noticed that stars twinkle. This twinkling is caused by turbulence in Earth's atmosphere. Pockets of air at different temperatures act like weak lenses, bending starlight in random directions. The effect causes stellar images to dance around on the detector, blurring out the precise position that astronomers are trying to measure. Professional observatories are located on mountaintops, partly to minimize this atmospheric blurring. Higher altitude means less atmosphere above the telescope, and mountain sites often have particularly stable air. Places like Mauna Kea in Hawaii, Cerro Paranal in Chile, and La Palma in the Canary Islands are prized for their exceptional atmospheric conditions. Even so, the atmosphere remains a fundamental limit for ground-based astrometry. This is why space-based observations transform the field. Above the atmosphere, there is no twinkling. Stellar images are sharp and stable. Positions can be measured with precision impossible from the ground. The Hipparcos satellite, launched in 1989, operated in Earth orbit for about 3.5 years. During that time, it measured the positions, parallaxes, and proper motions of over 100,000 stars. The Hipparcos catalogue remains a landmark achievement. For the first time, astronomers had a reliable three-dimensional map of the solar neighborhood, stretching out to several hundred parsecs in every direction. Stars that had previously been mere points of light now had known distances. The structure of the nearby galaxy began to come into focus, but Hipparcos was just a first step. The Gaia mission, launched in 2013, is a far more ambitious project. While Hipparcos measured about 100,000 stars, Gaia is measuring roughly 2 billion. While Hipparcos could detect parallaxes down to about 1 millisecond, Gaia can detect parallaxes down to about 20 microarcseconds, a factor of 50 more precise. While Hipparcos mapped the immediate solar neighborhood, Gaia is mapping a substantial fraction of the entire Milky Way galaxy. The Gaia spacecraft orbits at a special point called L2, about 1.5 million kilometers from Earth in the direction opposite the Sun. This location is ideal for astronomy because the spacecraft stays in permanent shadow, shielded from the Sun by Earth. The thermal environment is stable, which helps maintain the precise optical alignment needed for such delicate measurements. The view of the sky is unobstructed by Earth or Moon, allowing nearly continuous observations. Gaia's design is ingenious. The spacecraft contains 2 telescopes pointing in different directions, separated by a fixed angle of about 106 degrees. As Gaia slowly rotates, spinning once every 6 hours, these telescopes sweep across different parts of the sky. Over the course of its mission, Gaia observes every star multiple times, building up a comprehensive picture of stellar positions and motions. The data processing is staggering in scope. Each star is observed dozens of times over the mission lifetime. Each observation records the position of the star on Gaia's detectors with sub-pixel precision. These individual measurements are combined into a single catalogue that gives the position, parallax, proper motion, and brightness of each star. For a subset of stars, Gaia also measures the spectrum, revealing the star's temperature, composition, and radial velocity. The Gaia data releases have transformed stellar astronomy. The first release came in 2016, containing rough positions for about 1 billion stars. The second release in 2018 added parallaxes and proper motions for over 1 billion stars. The third release, which came in parts between 2020 and 2022, contains even more precise measurements along with additional data products like stellar classifications and orbital solutions for binary stars. What have we learned from Gaia? The answer would fill many books. We have learned that the Milky Way's spiral arms are more complex than previously thought, with spurs and branches and tangles that defy simple geometric models. We have found streams of stars left behind by globular clusters torn apart by the galaxy's gravity. We have traced the merger history of the Milky Way, identifying debris from galaxies absorbed billions of years ago. We have measured the mass of the galaxy by observing how far stars orbit around the center. We have discovered millions of variable stars, eclipsing binaries and other exotic objects. All of this flows from parallax. All of this rests on the parsec. Without distances, the stars would remain scattered across a flat sky. With distances, they become members of a three-dimensional structure, a swirling disk of stars and gas, orbiting a central concentration of matter. The parsec transforms astronomy from geometry to geography. Let us now consider some of the individual stars whose parallaxes have been measured and whose distances are known. The nearest star to Earth after the Sun is Proxima Centauri. This is a small red dwarf star, much cooler and dimmer than the Sun. It is part of the Alpha Centauri system, which also contains two larger stars called Alpha Centauri A and Alpha Centauri B. Proxima orbits the larger pair at an enormous distance, taking hundreds of thousands of years to complete one circuit. Proxima Centauri sits at a distance of about 1.3 parsecs, or 4.24 light-years. Its parallax is about 0.768 arcseconds, making it one of the easiest stars to measure. In fact, Proxima was not discovered until 1915, despite being the closest star to the Sun. Its extreme dimness made it invisible to earlier observers. Today we know that Proxima hosts at least two confirmed planets, one of which orbits in the habitable zone where liquid water might exist. The Alpha Centauri pair sits slightly further away at about 1.34 parsecs. These are Sun-like stars, much easier to see than Proxima. Alpha Centauri A is slightly larger and brighter than the Sun, while Alpha Centauri B is slightly smaller and dimmer. The two stars orbit each other every 80 years or so, swinging between about 11 AU at their closest and 36 AU at their farthest. The third nearest star system is called Barnard's star. This is another red dwarf, located about 1.83 parsecs from Earth. Barnard's star is famous for having the highest proper motion of any star in the sky. It moves across our field of view at about 10 arcseconds per year, fast enough that its motion is noticeable in photographs taken just a few years apart. This high speed is partly due to the star's proximity and partly due to its actual velocity through space relative to the Sun. Barnard's star also has historical significance in the parallax story. In 1916, the astronomer E. Barnard measured its parallax and discovered just how close it was. This made it an obvious target for searches for planets. In the 1960s, another astronomer named Peter van der Kamp claimed to have detected a planet around Barnard's star by observing tiny wobbles in its position. Unfortunately, these wobbles turned out to be instrumental artifacts, and the planet was never confirmed. More recent observations have suggested there might be a planet after all, though the matter remains debated. Beyond these nearest neighbors, the stellar census expands rapidly. Within 10 parsecs of the Sun, there are about 300 known stellar systems containing over 400 individual stars. Most of these are red dwarfs, dim and unassuming, invisible to the naked eye. A few are Sun-like stars. A handful are white dwarfs, the burnt-out remnants of stars that have exhausted their nuclear fuel. The solar neighborhood is a diverse collection of objects at various stages of stellar life. Within 100 parsecs, the number grows to tens of thousands of stars. At this distance, we start to encounter some of the bright naked eye stars that dominate our constellations. Sirius, the brightest star in the night sky, sits at about 2.6 parsecs. Vega, one of the stars in the Summer Triangle, is at about 7.7 parsecs. Arcturus, the brightest star in the northern spring sky, is at about 11 parsecs. Capella, the brilliant star that dominates winter evenings, is at about 13 parsecs. These stars are the local landmarks of our cosmic neighborhood. They are the stars our ancestors named, the stars that guided navigators across oceans, the stars that appear in myths and legends from every culture on Earth. And now we know exactly where they are. We know how many parsecs separate us from Sirius. We know the distance to Vega down to a fraction of a light year. The parsec has taken these familiar beacons and placed them in a three-dimensional map. But the more distant stars are also revealing their secrets. Gaia has measured parallaxes for stars all the way across the Milky Way disk, thousands of parsecs from Earth. These measurements are less precise than those for nearby stars. Of course, a star at 10,000 parsecs shows a parallax of only about 0.1 milliarc seconds, at the very limit of what Gaia can detect. But even rough distances at these enormous ranges provide valuable information about the structure and dynamics of our galaxy. One of the most exciting discoveries from Gaia involves the history of the Milky Way. Our galaxy has not existed in isolation. Over billions of years, it has swallowed smaller galaxies, absorbing their stars and incorporating their mass. These merger events leave traces that can be detected if you know how to look. Stars from an accreted galaxy often share similar orbits and chemical compositions, distinguishing them from stars that formed in the Milky Way itself. Gaia data has revealed several major accretion events. One of the most significant is called the Gaia Enceladus sausage, named for its elongated distribution in velocity space. This was a dwarf galaxy roughly the size of the small Magellanic Cloud that collided with the Milky Way about 8 to 11 billion years ago. The collision transformed both galaxies, puffing up the Milky Way's disk and depositing a cloud of foreign stars that still orbit the galactic center today. Another structure revealed by Gaia is called the Sequoia Galaxy, another dwarf that was absorbed early in the Milky Way's history. And there are hints of even more events, a whole timeline of galactic mergers written in the orbits of stars. Without distances, none of this would be visible. The stars would blend into a featureless glow. With distances measured in parsecs, the individual threads of galactic history can be teased apart. Let us shift our attention now to larger scales. We have talked about individual stars within the Milky Way. But what about other galaxies? How do we measure distances to objects millions of parsecs away? I mentioned the cosmic distance ladder earlier, and I described Cepheid variables and type Ia supernovae. Let me expand on how these methods work in practice. The key concept is the standard candle, an object whose true brightness is known. If you know how bright something really is, you can figure out how far away it is by measuring how bright it appears. Cepheid variables are pulsating stars that change in brightness over periods ranging from a few days to several months. The relationship between period and luminosity is remarkably tight. A Cepheid that takes 10 days to complete one cycle has a predictable brightness. A Cepheid that takes 30 days has a different, also predictable brightness. This relationship was discovered over a century ago and has been refined ever since. To use Cepheids as distance indicators, you first observe the pulsation. Modern telescopes can detect Cepheids in galaxies tens of megaparsecs away, watching them brighten and dim over the course of several weeks. You measure the period carefully, perhaps observing for a few months to get a precise value. Then you look up the period-luminosity relationship to determine the star's intrinsic brightness. Finally, you compare that intrinsic brightness to the apparent brightness you observe and calculate the distance. The uncertainty in Cepheid distances comes from several sources. The period-luminosity relationship itself has some scatter, meaning Cepheids with the same period can differ slightly in brightness. The interstellar medium between us and the Cepheid absorbs some light, making the star appear dimmer and potentially leading to overestimated distances. The calibration of the relationship depends on parallax measurements to nearby Cepheids, so any errors in those parallaxes propagate through to the final distances. Despite these uncertainties, Cepheids remain one of the most important rungs on the distance ladder. They bridge the gap between the parallax method, which works out to a few kiloparsecs, and supernovae, which can be seen across gigaparsecs. Cepheids can be detected in galaxies throughout the local group and somewhat beyond, covering distances from tens of kiloparsecs to about 30 or 40 megaparsecs. Type Ia supernovae extend the reach much further. These explosions are visible across most of the observable universe. A Type Ia supernova at its peak brightness puts out roughly 5 billion times more light than the Sun. This makes it visible at distances where Cepheids are much too faint to detect. But using Type Ia supernovae as standard candles requires care. Not all Type Ia supernovae are exactly the same brightness. There is some variation related to how quickly the supernova fades after maximum light. Brighter supernovae tend to fade more slowly, while dimmer ones fade faster. This relationship, called the Phillips relation after the astronomer who discovered it, allows astronomers to standardize supernova brightnesses. By measuring the rate of decline, you can correct for the intrinsic variation and get more accurate distances. The calibration of Type Ia supernovae ultimately depends on Cepheids. You need supernovae that occur in galaxies close enough to contain measurable Cepheids. By comparing the Cepheid distance to the supernova brightness in the same galaxy, you calibrate the supernova scale. Then you can apply that calibration to supernova in more distant galaxies where Cepheids are invisible. This chain of calibration is the cosmic distance ladder in action. Each step depends on the ones below it. Parallax grounds the entire system, providing distances in parsecs that can be measured directly through geometry. Cepheids extend the reach to megaparsecs, calibrated by parallax to nearby Cepheids. Supernovae push out to gigaparsecs, calibrated by Cepheids in relatively nearby galaxies. At each step, uncertainties accumulate. Errors in parallax become errors in Cepheid calibration, which become errors in supernova distances. This is why improving parallax precision matters for the entire enterprise of cosmic cartography. There are other rungs on the distance ladder as well. The Tully-Fisher relation connects the rotation speed of a spiral galaxy to its luminosity. Faster rotating galaxies tend to be more luminous. By measuring the rotation speed from the Doppler shift of spectral lines, you can estimate the true brightness and hence the distance. This method works out to about 100 megaparsecs. The surface brightness fluctuation method uses the graininess of a galaxy's light. Nearby galaxies appear smooth because individual stars are resolved. More distant galaxies appear grainy because you are seeing the random clustering of unresolved stars. The amount of graininess depends on distance in a predictable way, allowing distance measurements out to about 50 megaparsecs. Globular cluster luminosity functions, planetary nebula luminosity functions, and other specialized techniques fill in gaps and provide cross-checks. Each method has its strengths and weaknesses. Each one depends on calibration from the rungs below, and all of them, ultimately, trace back to parallax and the parsec. The sheer effort involved in building this distance ladder is staggering. Astronomers have devoted careers to refining individual steps. They have spent decades arguing about systematic errors and calibration uncertainties. They have used the Hubble Space Telescope to observe Cepheids in distant galaxies, one precious orbit of telescope time at a time. They have launched space missions specifically to measure parallaxes with higher precision. The entire project is a monument to human determination to measure the universe. And the project is not finished. The Hubble tension. I mentioned earlier, the disagreement between different methods of measuring the expansion rate suggests that something is still not quite right. Either some step of the distance ladder has a subtle error, or our understanding of cosmology is incomplete. Resolving this puzzle will require even better measurements at every level, from nearby parallaxes to distant supernovae. Future missions will help. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will observe thousands of Type Ia supernovae and Cepheids with unprecedented precision. The Vera Rubin Observatory will discover millions of variable stars and track their brightness over time. New analysis techniques applied to Gaia data continue to squeeze out more accurate parallaxes. The distance ladder is being strengthened rung by rung. Let us also consider some of the profound questions that distance measurements help us answer. I mentioned dark energy, the mysterious force driving the acceleration of cosmic expansion. This discovery depended entirely on accurate distances to Type Ia supernovae. By measuring how far away these supernovae were and comparing to their redshifts, astronomers found that the expansion of the universe is speeding up rather than slowing down. The redshift deserves explanation. When a galaxy moves away from us, the light it emits is stretched to longer wavelengths. Blue light becomes redder. This shift can be measured precisely by looking at spectral lines, the fingerprints of elements in the galaxy's stars. The more a galaxy's light is redshifted, the faster it is moving away from us. In an expanding universe, more distant galaxies are moving away faster. This relationship between distance and recession speed is called Hubble's law, after Edwin Hubble, who discovered it in 1929. Hubble's law implies that the universe is expanding uniformly in all directions. Space itself is stretching, carrying galaxies apart like raisins in rising bread. But the details of this expansion tell us about the contents of the universe. A universe filled only with matter would expand at a rate that slows over time. Gravity would pull everything back, decelerating the expansion. A universe with dark energy behaves differently. The dark energy provides a kind of repulsive gravity that pushes space apart faster and faster. The supernova observations in the late 1990s showed that distant supernovae were dimmer than expected. They were further away than Hubble's law without acceleration would predict. This could only be explained if the expansion rate was lower in the past, meaning the expansion has sped up over time. Dark energy was the explanation. This discovery earned the 2011 Nobel Prize in Physics. It reshaped our understanding of the cosmos, and it rested entirely on the ability to measure distances to supernovae millions of parsecs away. Without the cosmic distance ladder, without the foundation of parallax, without the parsec, we would never have known that the universe is accelerating. Distance measurements also reveal the geometry of the universe. Einstein's theory of general relativity predicts that matter and energy curve the fabric of spacetime. On cosmic scales, this curvature affects how distances grow with redshift. A universe with more matter curves one way, a universe with less matter curves another way, and a universe with exactly the right amount of matter is flat, like an infinite sheet. Observations of the cosmic microwave background and the distribution of galaxies show that the universe is very close to flat. The sum of matter, and dark energy adds up to exactly the critical density needed for flatness. This is a remarkable coincidence, and theorists are still trying to understand why the universe should have this property. Measuring cosmic flatness requires knowing distances with some precision. You need to compare the observed positions of galaxies and the patterns in the CMB to theoretical predictions for different geometries. The closer the measurements match the flat universe prediction, the more confident we are that flatness is real. All of this depends on the distance ladder. Another profound implication of distance measurements concerns the age of the universe. If you know how fast the universe is expanding and how that expansion rate has changed over time, you can run the clock backward to find when everything was compressed into a single point. This is the Big Bang, the origin of space and time as we know it. Current measurements indicate that the universe is about 13.8 billion years old. This age comes from fitting cosmological models to observations, including distance measurements to supernovae, the pattern of the CMB, and the clustering of galaxies. The parsec, as the foundation of distance measurement, contributes indirectly to this age estimate. Think about what this means. By measuring tiny angles in the sky, by defining a unit called the parsec, by climbing the cosmic distance ladder one rung at a time, we have figured out how old the universe is. We have traced the history of everything back to a singular event, nearly 14 billion years in the past. We have done this from a small planet orbiting an ordinary star in an unremarkable corner of the galaxy. The parsec connects our humble position to the grandest questions about existence. Let us also appreciate the beauty of the mathematical relationships involved. I mentioned that distance in parsecs equals 1 divided by parallax in arcseconds. This simple formula encapsulates the entire principle of parallax measurement. There is no conversion factor, no complicated coefficient, just a reciprocal relationship. The parsec was chosen specifically to make this formula as simple as possible, but the simplicity hides layers of meaning. The formula works because of how angles relate to distances in a triangle. When the parallax is 1 arcsecond, the distance is 1 parsec by definition. When the parallax is half an arcsecond, the star is twice as far, because the angle has shrunk by half for the same baseline. When the parallax is 1/10 of an arcsecond, the star is 10 times further. The formula captures this inversely proportional relationship. There is elegance in this design. The early astronomers who defined the parsec understood that a unit should work well with its measurement technique. They chose the arcsecond as the angular unit because it was a natural scale for parallax observations. They defined the parsec to match, creating a system where the math is clean and intuitive. Compare this to the light year. To convert a parallax into a distance in light years, you need a conversion factor. 1 parsec equals 3.26 light years. This factor is not round because the light year was defined independently of parallax. The two units come from different philosophical traditions, one rooted in observation and one rooted in physics. Both are valid, but the parsec fits the measurement process more naturally. This is why astronomers use parsecs in their research. When you are processing Gaia data, calculating distances for millions of stars, you want the simplest possible formula. You want to invert each parallax and get a distance directly. Converting to light years would add an extra multiplication at every step, introducing opportunities for error and slowing down the computation. The parsec is computationally efficient as well as conceptually appropriate. Let me tell you about a few more remarkable stars and what their distances reveal. Consider Betelgeuse, the red supergiant in the constellation Orion. This star is enormous, so large that if you placed it at the center of our solar system, its surface would extend beyond the orbit of Jupiter. Betelgeuse is also nearing the end of its life, destined to explode as a supernova sometime in the next 100,000 years or so. The distance to Betelgeuse has been surprisingly difficult to pin down. Early estimates range from about 100 to 200 parsecs. More recent measurements using radio interferometry suggested around 220 parsecs. Gaia data has been tricky to interpret because Betelgeuse is so bright that it saturates the detectors. Current best estimates place it at around 160 to 170 parsecs, though some uncertainty remains. Why does the distance to Betelgeuse matter? Because it affects our understanding of the star itself. The true brightness of a star depends on its distance. If Betelgeuse is further than we thought, it must be more luminous than we thought. This in turn affects our models of stellar evolution, our predictions for when it might explode, and our estimates of how bright the supernova will appear from Earth. Another fascinating star is Polaris, the current North Star. Polaris is actually a triple star system, with a bright Cepheid variable as the primary star. Its distance has been measured using both parallax and the Cepheid period luminosity relation, providing a cross-check between methods. The Hipparcos satellite measured a parallax that implied a distance of about 133 parsecs. Gaia refined this to about 123 parsecs. Meanwhile, the Cepheid method gave a slightly different answer, around 99 parsecs, depending on which calibration was used. This discrepancy is part of a larger debate about the Cepheid distance scale. Small differences in how the period luminosity relation is calibrated can lead to different distances for individual stars. These differences accumulate as you climb the distance ladder, potentially affecting measurements of cosmic expansion. The Polaris system is one of the benchmarks used to investigate these issues. Rigel, another star in Orion, illustrates the challenge of measuring distances to very distant stars. Rigel is a blue supergiant, extremely luminous but quite far away. Early estimates placed it at around 240 parsecs. Gaia data suggests it might be closer to 270 parsecs, though the uncertainty is substantial. For a star this luminous, even small errors in distance propagate into large errors in estimated brightness and mass. These examples show that distance measurement remains an active area of research. The parsec is not just a historical artifact. It is a living tool being refined and applied with ever greater precision. Each new satellite, each new observation campaign, each new analysis technique pushes our knowledge a little further. The map of the cosmos grows more accurate with every passing year. Before we conclude, let me offer one more perspective on why the parsec matters. Throughout this exploration, I have emphasized the technical utility of the parsec, its role in measurement and calibration. But there is also a philosophical dimension worth considering. The parsec represents a certain kind of humility. It acknowledges that the cosmos operates on scales vastly different from human experience. It does not try to domesticate the universe by expressing everything in familiar units. Instead, it accepts the strangeness of cosmic distances and develops concepts appropriate to that strangeness. The parsec is a tool for engaging with the universe on its own terms. At the same time, the parsec represents a certain kind of ambition. It says that even the strangest, most inhuman scales can be measured and understood. The universe may be vast beyond imagination, but it is not beyond inquiry. By developing the parallax method, by defining the parsec, by building space telescopes to measure micro-arcsecond angles, we have extended our reach across billions of light years. The parsec is a monument to human curiosity. There is a tension here that runs through all of science. On one hand, nature is what it is, indifferent to human preferences. We must accept reality as we find it, not as we might wish it to be. On the other hand, understanding is possible. Through careful observation and rigorous thinking, we can comprehend aspects of reality that lie far beyond direct experience. The parsec embodies both sides of this tension. It is strange because the universe is strange. It is comprehensible because the universe ultimately follows laws we can discover. This is perhaps the deepest lesson of the Parsec. The cosmos is vast and impersonal, operating on scales that dwarf every human concern. But it is not hostile. It does not hide its secrets behind impenetrable walls. For those willing to do the hard work of observation and analysis, the universe reveals itself. Distances can be measured, structures can be mapped, history can be traced. The Parsec is our key to this revelation. So as we finally bring this exploration to a close, I hope you carry with you a new appreciation for this strange unit of distance. The Parsec is more than a number. It is a connection between the geometry of triangles and the expansion of the universe. It is a link between the tiny angle of an arc-second and the vast gulfs between galaxies. It is evidence that human beings, for all our limitations, can understand a universe that never evolved us to understand it. The next time you read about a star at 10 parsecs or a galaxy at 20 megaparsecs, pause for a moment. Remember the parallax technique. Remember the cosmic distance ladder. Remember the centuries of work that went into defining and measuring these distances. And remember that every number represents a triumph of curiosity over limitation, a small victory against the immensity of the night. The stars are far, the galaxies are further. The edge of the observable universe lies at the limit of comprehension. But we know how far they are. We can write the distances in parsecs. We can plot the positions on maps. We have made the strange familiar enough to measure, even if it remains too strange to truly feel. And that is the gift of the Parsec. It gives us the cosmos, not as we experience it, but as it actually is. But before we truly conclude, allow me to take you even deeper into the cosmic story. The Parsec has revealed so much, yet there is always more to explore. Let us venture further into the details of stellar parallax, galactic structure, and the grand architecture of the universe. Consider the practical challenges astronomers face when measuring parallax for very distant stars. As I mentioned, the parallax angle shrinks with distance. A star at 1,000 parsecs shows a parallax of only 1 milliarcsecond. A star at 10,000 parsecs shows a parallax of just 100 microarcseconds. These are angles so tiny that they push the limits of even space-based telescopes like Gaia. At such small angles, systematic errors become critical. The exact pointing of the telescope must be known to extraordinary precision. The distance between the two main mirrors on Gaia, which determines the basic angle between its two fields of view, must remain stable to within a few micrometers over years of operation. Thermal fluctuations, radiation pressure from sunlight, and tiny gravitational tugs from the moon and planets can all introduce errors. The Gaia team has developed sophisticated methods to track and correct these systematic effects. They use observations of quasars, extremely distant active galaxies that show no measurable parallax, as fixed reference points. Any apparent motion of quasars must be due to instrumental effects rather than actual parallax. By monitoring quasar positions, the team can calibrate out instrumental drifts. They also use the redundancy of millions of observations. Each star is observed dozens of times at different points in its orbit. By fitting all these observations simultaneously, the true parallax can be separated from noise and systematic effects. The mathematical machinery involved is staggering, requiring supercomputers to process the data and produce the final catalogue. The result is a precision that would have seemed miraculous to astronomers of earlier generations. Gaia routinely measures parallaxes to better than 100 microarcseconds for millions of stars. For the brightest stars, the precision reaches 20 or 30 microarcseconds. This corresponds to distance uncertainties of just a few percent at several kiloparsecs, a remarkable achievement. But even Gaia has limits. For stars at the far side of the galaxy, tens of thousands of parsecs distant, the parallax becomes too small to measure reliably. The measurement uncertainty becomes larger than the parallax itself, making the inferred distance meaningless. Beyond about 20 kiloparsecs, direct parallax measurement with current technology is essentially impossible. This is where the cosmic distance ladder becomes essential. We need other methods to reach beyond the parallax horizon. And those methods, as I have explained, ultimately depend on parallax for their calibration. The Cepheids that carry us to megaparsec distances were calibrated by nearby Cepheids with measured parallaxes. The Typoia supernovae that carry us to gigaparsec distances were calibrated by Cepheids in their host galaxies. There is a beautiful recursion in this structure. Each rung of the ladder reaches further than the last, but each rung depends on all the rungs below. Improve the precision of parallax measurements, and you improve the calibration of Cepheids. Improve the Cepheid calibration, and you improve the supernova distances. Improve the supernova distances, and you sharpen your picture of cosmic expansion and dark energy. This interconnection means that advances in one area propagate through the entire system. When Gaia produced its latest data release, cosmologists immediately began updating their distance measurements throughout the observable universe. The ripples spread outward from our local neighborhood to the most distant galaxies ever observed. Let us also consider some of the stars and stellar systems that have proven especially valuable for understanding the cosmic distance scale. I mentioned Polaris earlier. Another important calibrator is Delta Cephei, the prototype of the Cepheid variable class. This star pulsates with a period of about 5.4 days, brightening and dimming in a remarkably regular cycle. Its distance has been measured through multiple methods, including parallax, providing a critical anchor for the Cepheid period luminosity relation. RS Puppis is another notable Cepheid, surrounded by a spectacular nebula of gas and dust. Light from the star's pulsations echoes off this nebula, creating rings of illumination that expand outward over time. By tracking these light echoes, astronomers can measure the distance to the star geometrically, independent of parallax. The result provides a cross-check on other distance methods. In the Large Magellanic Cloud, the eclipsing binary system known as OGLE, LMC, SC16, 10.5 has proven invaluable. Eclipsing binaries are pairs of stars that orbit each other in such a way that they periodically pass in front of each other as seen from Earth. By analyzing the eclipses, astronomers can determine the physical sizes of the stars. Combined with surface brightness measurements, this yields a geometric distance to the system. Such measurements help calibrate the distance to the Large Magellanic Cloud, which in turn calibrates the Cepheid scale. These individual stellar systems may seem like obscure astronomical trivia, but they are the foundation stones of our cosmic map. Every time you read that a galaxy is at such and such megaparsecs, or that the universe is a certain number of billion years old, those numbers trace back to careful measurements of stars like Delta Cephei and OGLE LMC SC16, 10.5. The Parsec connects us to these calibrators, and through them to the grandest questions of cosmology. Let me now turn to the structure of our own galaxy in more detail. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure from which spiral arms extend. We cannot see the overall shape directly because we are embedded within the disk. But by measuring distances to many stars and tracing their distribution, we can reconstruct the galaxy's form. The bar at the center of the Milky Way extends roughly 5 kiloparsecs in length. It tilts at an angle to our line of sight, so one end appears closer than the other. Stars in the bar follow elongated orbits that maintain the bar's shape over time. The bar channels gas toward the central regions, potentially feeding the supermassive black hole at the galactic core. Beyond the bar, the spiral arms wind outward through the disk. The major arms have been named after the constellations in which they appear most prominent from our vantage point. The Sagittarius arm, the Scutum Centaurus arm, the Perseus arm, and the outer arm are the primary features. Between these major arms lie smaller structures, spurs and branches that complicate the overall pattern. The Sun's position within this structure has been refined over decades of observation. Current estimates place us about 8 kiloparsecs from the galactic center, within a minor arm called the Orion Spur, or local arm. This spur connects to larger arms on either side, but it is not one of the dominant features of the galaxy. We are, in some sense, residents of a cosmic backwater, a minor branch rather than a main highway. This modest position has not prevented us from mapping the grand structure. Radio observations of hydrogen gas, which emits at a characteristic wavelength of 21 centimeters, have traced the spiral arms across the galaxy. Infrared surveys have penetrated the dust that obscures visible light, revealing stars on the far side of the galactic center. And now Gaia, with its billions of parallaxes, has produced three-dimensional maps of unprecedented detail. These maps reveal a dynamic, turbulent galaxy. The spiral arms are not static features. They are density waves that propagate through the disk, compressing gas and triggering star formation as they pass. Stars drift in and out of arms over millions of years, spending some time in the bright arm regions and some time in the dimmer inter-arm spaces. The galaxy churns and flows, a living system rather than a static sculpture. The halo of the Milky Way also reveals complexity when examined in detail. Old stars in the halo have lower metal content than stars in the disk. Metals, in astronomical jargon, refer to all elements heavier than helium. These elements are produced in stars and dispersed by supernovae. Low metal content indicates that a star formed early, before many generations of stars had enriched the galaxy with heavier elements. Halo stars also move differently than disk stars. While disk stars orbit the galactic center in roughly circular paths within the plane, halo stars follow elongated orbits that take them high above and below the disk. Some halo stars plunge through the disk on each orbit, spending most of their time in the sparse outer regions. Among the halo population are streams of stars, elongated structures that trace the orbits of disrupted globular clusters and dwarf galaxies. These streams are fossils of past accretion events. A small galaxy or cluster that ventured too close to the Milky Way was torn apart by tidal forces, its stars stretched into a ribbon that follows the original orbit. By mapping these streams, astronomers reconstruct the merger history of our galaxy. Gaia has discovered numerous new streams that were invisible before. Some are narrow and coherent, the remains of compact clusters. Others are broad and diffuse, the remnants of larger dwarf galaxies. The Sagittarius stream, associated with a dwarf galaxy that is still being absorbed by the Milky Way, wraps almost completely around the galaxy in a great arc. Other streams bear names like GD1, Chelum, and Orphan, each one a chapter in the story of galactic growth. All of this structure, from the spiral arms to the halo streams, is revealed through distance measurement. without knowing where stars are in 3 dimensions, we would see only a flat distribution of points on the sky. The parsec, as always, is the key that unlocks the 3rd dimension. Let us also consider what the parsec reveals about stellar populations. Stars come in many types, from hot blue giants to cool red dwarfs. The distribution of these types varies with location in the galaxy. Young, hot, massive stars concentrate in the spiral arms where star formation is active. Older, cooler, less massive stars populate the disk more uniformly. The halo contains mostly old stars, many of them low-mass red dwarfs or white dwarf remnants. By measuring distances to stars of different types, astronomers can trace these populations in 3 dimensions. The results confirm our understanding of stellar evolution and galactic dynamics. Massive stars form, live briefly, and die as supernovae within a few million years. They never stray far from their birthplaces in the spiral arms. Low-mass stars live for billions of years, time enough to wander across the galaxy and mix into the general disk population. White dwarfs, the remnant cores of dead stars, provide another window into galactic history. By measuring distances to white dwarfs and determining their temperatures, astronomers can estimate their ages. The oldest white dwarfs in the solar neighborhood have been cooling for 10 to 12 billion years, placing their formation in the earliest epochs of the Milky Way's existence. These ancient remnants are fossils from the galaxy's youth. Neutron stars and black holes are harder to study because they emit little or no visible light. But when they have companion stars, we can sometimes infer their distances from the companions. A few neutron stars have measurable parallaxes from radio observations using very long baseline interferometry, which achieves angular resolution far surpassing optical telescopes. These measurements place neutron stars within the context of the galactic map. The parsec thus extends not only across space, but across the full diversity of stellar objects. Baowen. From hot blue supergiants to cold brown dwarfs, from newborn protostars to ancient white dwarfs, distance measurement in parsecs puts everything in context. The galaxy becomes not just a collection of lights, but a structured ecosystem of stellar life. Now, let me return once more to the cosmic distance ladder and explore its furthest reaches, beyond type Eloia supernovae, which can be seen to distances of several gigaparsecs. Other techniques push even further. One such technique involves quasars, extremely luminous active galaxies powered by supermassive black holes, consuming vast quantities of gas. Quasars can be seen across most of the observable universe. Some lie at redshifts greater than 7, meaning their light has been traveling for more than 90% of cosmic history. But using quasars as distance indicators is challenging because their luminosities vary enormously. Unlike type Ia supernovae, there is no simple relationship between observable properties and intrinsic brightness. Nevertheless, astronomers have developed ways to use quasars for cosmology. One approach involves the time delay between multiple images of gravitationally lensed quasars. When a foreground galaxy bends the light from a distant quasar, it can create multiple images that reach us along slightly different paths. Variations in the quasar's brightness appear in each image at different times, and the time delay depends on the geometry of the lens system, which in turn depends on distances. By measuring these delays, astronomers can constrain the cosmic expansion rate. Another approach involves the cosmic microwave background itself. The CMB provides a standard ruler of sorts. The characteristic size of temperature fluctuations in the CMB corresponds to the sound horizon at the moment of recombination, when atoms first formed and light began traveling freely. This size can be calculated from physics and compared to the observed angular scale of the fluctuations. The comparison yields a distance to the CMB surface, roughly 46 billion light-years in proper distance, corresponding to a look-back time of 13.8 billion years. This CMB measurement anchors the far end of the cosmic distance ladder. It provides an independent check on distances derived from supernovae and other local methods. When the two approaches agree, we gain confidence that our understanding of cosmic expansion is correct. When they disagree, as they currently do in the form of the Hubble tension, we learn that something in our picture needs revision. The resolution of the Hubble tension will likely require better measurements at many levels. Improved parallaxes from future space missions will refine the Cepheid calibration. More precise observations of Cepheids and supernovae will reduce scatter in the distance ladder. Better understanding of systematic errors in CMB analysis will sharpen that end of the comparison. The Parsec sits at the beginning of this chain, the first solid ground from which all else extends. As we truly bring this exploration to a close, let me offer a final reflection on the wonder of what we have discussed. The Parsec began as a practical solution to a measurement problem. Astronomers needed a unit that matched their technique, and the Parsec was the natural choice. But what started as practical has become profound. The Parsec connects the geometry of triangles to the expansion of the cosmos. It links the width of Earth's orbit to the edges of the observable universe. It embodies human ambition to understand a universe that operates on scales far beyond human experience. Every parsec measured represents a triumph of ingenuity over limitation. The stars are far, but we have learned their distances. The galaxies are further, but we have mapped their positions. The universe is old, but we have traced its history. None of this was inevitable. It required centuries of effort, the development of ever more sophisticated instruments, and the courage to trust in methods that our intuitions cannot verify. The Parsec is a symbol of this achievement. It is strange, yes. It defies easy visualization, but it works. It has carried us from the first hesitant measurements of nearby stars to the discovery of dark energy and the detailed mapping of cosmic structure. It will continue to serve as we push toward ever greater precision and ever more distant horizons. So the next time you look up at the night sky, remember the Parsec. Remember that those points of light are not merely scattered across a flat canvas. They are arranged in three-dimensional space, at distances measured in parsecs and kiloparsecs and megaparsecs. They are suns, worlds, galaxies, each one at a known location in the cosmic map. The Parsec has given us this knowledge, transforming wonder into understanding, mystery into measurement. Thank you for staying with us through this journey. The universe is full of wonders, and the Parsec helps us find them all. Keep exploring, keep wondering, and keep looking up at those distant points of light, each one a sun, each one at a measurable distance, each one part of the great cosmic tapestry that the Parsec helps us see. Yet there is still more to tell. The story of the Parsec weaves through every branch of modern astronomy, touching questions both practical and profound. Let us continue a little longer, exploring some of the frontiers where the Parsec remains essential. Consider the search for exoplanets, worlds orbiting stars other than the Sun. This search has exploded in recent decades, revealing thousands of planets around other stars. Many detection methods depend on knowing the distances to the host stars, and thus on the Parsec. The transit method, which watches for the dimming of starlight as a planet crosses in front of its star, tells us the ratio of planet size to star size. But to know the actual size of the planet, we need to know the size of the star. And to know the size of the star, we often need to know its distance. A star that appears a certain brightness at a certain distance has a calculable luminosity, and luminosity relates to size through the laws of physics. The parsec enters this chain of reasoning, connecting what we observe to what we want to know. The radial velocity method, which detects the wobble of a star caused by an orbiting planet, tells us the minimum mass of the planet. But characterizing the star itself, understanding its mass and radius and temperature, often requires knowing its distance. The parsec again provides the key. Gaia's precise parallaxes have transformed exoplanet science. By providing accurate distances to millions of potential host stars, Gaia enables better characterization of every planet detected around those stars. We can say with greater confidence how large a planet is, how massive it might be, and whether it lies in the habitable zone where liquid water could exist. The parsec helps us assess the habitability of distant worlds. The astrometric method of planet detection, which looks for the tiny positional wobble of a star caused by an orbiting planet, is particularly dependent on precise distance measurements. The wobble appears as a tiny angular motion on the sky. To convert this angle into a physical distance, you need to know how far away the star is. A wobble of 1 microarcsecond corresponds to different physical displacements at different distances. The parsec allows us to translate angular measurements into physical conclusions about planetary systems. Gaia itself has begun detecting planets through the astrometric method. For nearby stars, the wobble induced by a Jupiter-mass planet is detectable in Gaia's data. Several candidate planets have already been announced, though confirmation requires additional observations. As the mission continues and data analysis improves, more planets will emerge from the astrometric signal. Each detection will depend on the parallax distance that places the star in context. Let us also consider stellar evolution, the study of how stars change over their lifetimes. Stars are born in clouds of gas, spend most of their lives fusing hydrogen in their cores, and eventually die in ways that depend on their mass. Understanding this process requires comparing observed stars to theoretical models, and that comparison depends critically on knowing stellar distances. When astronomers plot stars on a diagram showing luminosity versus temperature, they obtain the famous Hertzsprung-Russell diagram. Main sequence stars, which are fusing hydrogen in their cores, form a diagonal band across this diagram. Giants and supergiants, which have evolved beyond the main sequence, appear in other regions. White dwarfs, the remnants of dead stars, cluster in a corner. The position of a star on this diagram depends on its absolute luminosity, which requires knowing its distance. The Hertzsprung-Russell diagram only makes sense when distances are known. Before parallax measurements were available, astronomers had to guess which stars were intrinsically luminous and which were nearby. The diagram was fuzzy and uncertain. With precise distances, it becomes a sharp, powerful tool for understanding stellar physics. Gaia has produced the most precise Hertzsprung-Russell diagram ever constructed. With parallaxes for millions of stars, the main sequence appears as a razor-thin line rather than a diffuse band. Fine structure becomes visible that was previously lost in distance uncertainty. Binary stars, variable stars, and peculiar objects reveal themselves through their positions on the diagram. The parsec has sharpened our view of stellar evolution. Open clusters, groups of stars that form together from the same cloud, provide another application. All stars in an open cluster are at essentially the same distance from us. By measuring the parallax to any cluster member, we obtain the distance to the entire cluster. This allows us to study the Hertzsprung-Russell diagram for a population of stars with the same age and initial composition. The comparison to theoretical models tests our understanding of stellar evolution. Gaia has measured parallaxes to members of many open clusters. The results confirm the distances obtained through earlier methods while dramatically improving precision. In some cases, Gaia has revealed that clusters previously thought to be single entities are actually multiple groups at different distances, projected onto the same region of sky by chance. The Parsec helps disentangle these superpositions. Globular clusters, older and more massive than open clusters, present different challenges. They lie at greater distances, typically several kiloparsecs, where parallax measurement is less precise. Nevertheless, Gaia has improved our knowledge of globular cluster distances, refining the ages and other properties inferred from their stellar populations. The oldest globular clusters contain stars that formed in the first billion years of the universe, and their distances place them in the context of galactic history. The study of the interstellar medium, the gas and dust between the stars, also benefits from distance measurements. Dust along our line of sight absorbs and scatters starlight, making stars appear dimmer and redder than they truly are. This extinction complicates the interpretation of stellar observations. But if we know the distances to many stars, we can map the three-dimensional distribution of dust. Nearby stars suffer less extinction than distant stars, and by comparing them, we can locate the dust. Gaia data has produced three-dimensional maps of interstellar dust, extending several kiloparsecs from the Sun. These maps reveal the structure of the local interstellar medium, including bubbles cleared by supernova explosions and dense clouds where new stars are forming. The local bubble, a cavity of hot, thin gas surrounding the Sun, appears clearly in these maps. Its boundaries, where the gas becomes denser, have been traced using stellar distances. Dark clouds, regions so dense with dust that they block the light from background stars, have also been mapped in 3 dimensions. Famous star-forming regions like the Orion Nebula and the Taurus molecular cloud now have precise distances, placing them in context within the galaxy. The Orion Nebula lies about 400 parsecs away. The Taurus clouds are closer, at roughly 140 parsecs. These distances matter for understanding the physical conditions in these regions and the stars and planets forming within them. Let me also mention the importance of the parsec in gravitational wave astronomy, a new field that has emerged only in recent years. Gravitational waves are ripples in space-time produced by accelerating masses. The first direct detection came in 2015, when the LIGO Observatory recorded waves from 2 merging black holes over 1 billion light-years away. Gravitational wave detectors measure the strain of space-time, the fractional change in distance caused by a passing wave. This strain depends on the intrinsic strength of the source and the distance to the source. To interpret the observations, astronomers need to estimate how far away the source was. For most gravitational wave events, this distance comes from the waveform itself, which encodes information about the masses and orientations of the merging objects. But for some events, independent distance measurements are possible. When gravitational waves are accompanied by electromagnetic signals, such as light from a neutron star merger, the host galaxy can be identified. The distance to that galaxy, measured through the cosmic distance ladder, provides a cross-check on the gravitational wave distance. In 2017, the merger of 2 neutron stars produced both gravitational waves and a visible counterpart. The host galaxy, NGC 4993, lies about 40 megaparsecs away. This distance, ultimately rooted in the parsec, provided a crucial calibration for gravitational wave cosmology. Such events allow an independent measurement of the cosmic expansion rate. The gravitational wave amplitude gives a distance, and the galaxy redshift gives a recession velocity. Combining them yields the Hubble constant, the rate at which the universe is expanding. This method, called the standard siren technique, provides a check on traditional distance ladder methods. Currently, the uncertainties are large because few events have been detected with electromagnetic counterparts. But as more events accumulate, standard sirens will become an important cosmological tool. The future holds exciting prospects for distance measurement. The Nancy Grace Roman Space Telescope will survey large portions of the sky at infrared wavelengths, detecting Cepheids and supernovae in thousands of galaxies. The Vera Rubin Observatory will discover millions of transient events, including many type Ia supernovae, that can serve as distance indicators. New space missions may extend parallax measurements to even greater precision. There is ongoing work to improve the analysis of existing data as well. Sophisticated statistical techniques are being developed to extract more information from Gaia observations. Machine learning algorithms are helping to identify patterns in the data that traditional methods might miss. The community is continually refining the distance ladder, reducing uncertainties at each rung, and propagating those improvements outward. The Hubble tension remains a major driver of this effort. The disagreement between early universe and late universe measurements of the expansion rate is roughly 5%. This may not sound like much, but the statistical significance is high enough to suggest a real problem. Either some systematic error is lurking in one or more measurement techniques, or our cosmological model is missing something. Resolving this question will require the best possible distance measurements at every scale. Some researchers have proposed new physics to explain the tension. Perhaps the early universe behaved differently than our models assume. Perhaps dark energy is not constant, but varies with time. Perhaps there are additional relativistic particles in the early universe that affect the expansion rate. Each of these possibilities has implications that can be tested with better observations. The parsec, through the distance ladder it anchors, will play a role in distinguishing these scenarios. As we finally conclude, let us remember what the parsec has taught us. The universe is vast, far larger than any human experience prepared us to imagine. But this vastness is not chaos. It is structured, ordered, and ultimately comprehensible. The parsec is one of the tools that makes this comprehension possible. It takes the impossibly large and makes it measurable. From the first parallax measurement in 1838 to the billions of distances in the Gaia catalogue, the story of the parsec is a story of human ingenuity and persistence. We have overcome the limitations of our senses and the boundaries of our planet to measure distances that stretch across the cosmos. We have built telescopes in space and developed mathematical techniques of extraordinary sophistication. We have traced the cosmic distance ladder from nearby stars to the edge of the observable universe. And we are not done. The future will bring better measurements, deeper understanding, and new discoveries that we cannot yet foresee. The parsec will remain at the foundation, the starting point, from which all else extends. It is a humble unit in some ways, just a relationship between an angle and a baseline. But from that humble beginning flows our entire map of the universe. Thank you for accompanying us on this exploration. May the parsec serve you well as you continue to explore the cosmos. May you find wonder in the distances between the stars. And may you remember that every point of light in the night sky has a location, a distance, a place in the great map that humanity has constructed through centuries of careful work. The Parsec makes this knowledge possible. And that knowledge, strange and inhuman as its scale may be, is one of the greatest achievements of our species. Keep looking up. The stars are far, measured, in parsecs, but they are not beyond our understanding. The universe is vast, but it is knowable. And knowing it, truly seeing the order within the immensity, is among the deepest joys that human experience can offer. The Parsec is our enduring guide to that joy. Use it well. And yet, there remains one more thread to weave into this cosmic tapestry. We have spoken of distances and techniques, of ladders and calibrations. But let us also speak of the people who made this possible. Science is a human endeavor, and the story of the Parsec is ultimately a story of human beings striving to understand their place in the universe. Think of Friedrich Bessel, working through cold German nights with his heliometer, making painstaking measurements of tiny stellar positions. He did not know if his effort would succeed. For centuries, astronomers had tried and failed to detect stellar parallax. The angles were simply too small. But Bessel persisted, choosing his target carefully, refining his technique, checking and rechecking his data. When he finally published his parallax for 61 Cygni in 1838, he gave humanity its first true measure of interstellar distance. Think of Henrietta Swan Leavitt, working at Harvard College Observatory in the early 1900s. She was hired as a human computer, one of many women who performed the tedious work of measuring stellar brightnesses from photographic plates. Her work was considered menial, unsuitable for the grander theorizing reserved for male astronomers. Yet in her careful measurements of Cepheid variables in the Magellanic Clouds, she discovered a relationship that would unlock the universe. The period luminosity relation she found made it possible to measure distances far beyond the reach of parallax. Leavitt never received the recognition she deserved during her lifetime. She died in 1921, before the full implications of her discovery became clear. But every distance measured to a galaxy traces back to her work. She saw further than anyone before her, not through better telescopes, but through more careful analysis of the data at hand. Think of Edwin Hubble, using the 100-inch telescope on Mount Wilson to observe faint smudges of light. He found Cepheid variables in the Andromeda Nebula, and using Leavitt's relation, calculated a distance of nearly 1 million light-years. This proved that the nebula was a separate island universe, a galaxy in its own right. The universe suddenly became far larger than anyone had imagined. These pioneers worked without computers, without space telescopes, without many tools we take for granted today. They measured angles by eye, reduced data by hand, and built their understanding one observation at a time. They laid the foundation on which all subsequent work has built. Today, the Gaia spacecraft carries that tradition into the 21st century. The satellite works autonomously, spinning slowly in space, sweeping its twin telescopes across the sky. It measures the positions of stars automatically, transmitting data back to Earth for processing. No human eye looks through Gaia's optics. No hand adjusts its focus. Yet the same principles that guided Bessel are encoded in its operation. Parallax remains parallax, whether measured by a 19th century astronomer, squinting through an eyepiece, or by a robotic satellite 1 million kilometers from Earth. The Gaia team comprises hundreds of scientists and engineers from across Europe. They have dedicated years of their careers to building, operating, and analyzing the mission. Their collective contribution is no less significant than the famous pioneers. They have mapped billions of stars and produced a catalogue that will serve astronomy for generations. This is how science truly advances. Each generation builds on the work of those who came before. Each new measurement refines and extends understanding. The parsec, defined over a century ago, remains the standard because it works. Let us also remember that science is international. The Gaia mission is led by the European Space Agency, but it benefits from contributions worldwide. The analysis draws on techniques developed across many countries. The data serves astronomers everywhere, regardless of nationality. When we measure a distance in parsecs, we participate in a global enterprise that transcends borders. This international cooperation extends throughout the cosmic distance ladder. American telescopes observe cepheids in distant galaxies. Japanese astronomers study supernovae. Australian facilities contribute to surveys. The data flow across continents, combined into a unified picture of the cosmos. There is inspiration in this. At a time when the world often seems divided, science offers an example of productive cooperation. The universe does not care about human politics. The parallax angle of a star is the same whether measured from Germany or Japan or Chile. The parsec also reminds us of the value of patience. The distance ladder was not built in a year or a decade. It took centuries, accumulating one measurement at a time, one calibration at a time. Errors were made and corrected. Techniques were developed and refined. The understanding we have today is the product of countless hours of work by thousands of individuals, most of whom will never be remembered by name. Yet their contributions endure in the precision of our cosmic map. This patience is worth emulating. In a culture that often prioritizes quick results, science offers a different model. Some questions take generations to answer. The parsec teaches us to value incremental progress, to trust that careful work accumulates into genuine understanding. And what understanding it provides. We know where the stars are. We know how far to the galaxies. We know the size and age of the observable universe. We know that space is expanding, that dark energy is pushing things apart, that our cosmos has a history stretching back nearly 14 billion years. All of this knowledge rests on the parsec and the distance ladder it supports. This knowledge changes how we see our place in existence. We are not at the center of the universe. We are not even at the center of our own galaxy. We occupy a small planet orbiting an ordinary star in a minor arm of a typical spiral galaxy, one among hundreds of billions of galaxies in the observable universe. The parsec has shown us our cosmic insignificance. Yet this insignificance is paired with something remarkable. We may be small, but we can understand the vastness that contains us. We may be brief, but we can trace histories spanning billions of years. The parsec gives us this dual perspective. It reveals both how little we are and how much we can know. It humbles us with scale while empowering us with comprehension. This is the gift of the parsec. It is more than a unit of measurement. It is a window onto the universe, a key to cosmic cartography, a symbol of human aspiration. Every distance given in parsecs carries within it the history of astronomy, the labor of generations, and the ambition to understand. As we part ways after this exploration, carry the parsec with you. Remember it when you read about newly discovered exoplanets orbiting stars a few parsecs away. Remember it when headlines announce galaxies at millions of megaparsecs. The parsec is there in the background, making all these discussions possible. And remember that you too are part of this story. By learning about the parsec, by understanding its meaning, you join the community of curious minds. who have looked up at the sky and wondered about distances. That community spans centuries and continents. Welcome to it. The universe awaits your continued exploration. The stars shine at their measured distances. The galaxies wheel majestically through the void at their calculated velocities. The Parsec gives order to this immensity, making the unimaginable almost imaginable. Almost. For the true scale of the cosmos will always exceed our intuitions. But we can approach it, respect it, and know it through the tools we have developed. The Parsec is one such tool. Use it, think with it, and let it carry you, in imagination if not in body, across the vast distances that fill our remarkable universe.